In the previous class, we saw that quantum confinement of electrons modify the density of states and energy levels of confined system. This modification produces a number of important manifestations in the electronic and optical properties of semiconductors. Such manifestations have found importance in technological applications. Today we are going to discuss the optical properties of such systems, which is important for photonic application. We have seen in previous two classes that quantum confinement leads to a blue shift in the band gap and the formation of discrete subbands along the direction of confinement. As the size of the confinement structure increases, the band gap decreases and finally approaches the bulk band gap value. Such band gap changes can be easily inferred from the optical absorption studies of quantum structures. As the size becomes smaller, the wavelength at which the optical absorption happens shifts to smaller wavelength side. Emission is also modified. As I mentioned in a previous class, the color of the emitted light depends on the band gap of the emitting material, and hence a change in the band gap of the material leads to change in the color of the light emitted from it. Thus, a bigger sized quantum dot structure with a small band gap emits light in the higher wavelength region, while an extreme confined structure emits light in the shorter wavelength region. Thus, it is possible for us to engineer a material for a required emission wavelength by simply changing the size of the materials. So let's discuss the optical manifestations of quantum confinement one by one. We saw in the previous classes that the quantum confinement produces a major modification in the density of states both for the valence and conduction bands. While we have a continuous smooth distribution of density of states for the bulk material, the states are squeezed in a narrow energy range for confined structures. This packing of energy states near the band gap becomes more pronounced as the dimensions of the confinement increases from quantum well to quantum wire to quantum dots. For quantum dots, the density of states has non-zero values only at discrete set of energies. Interband transitions are usually treated by using time-dependent perturbation theory. The transition rate from an initial state to a final state is given by the Fermi-Golden rule and it's given by this equation. Here H prime Vc is the matrix element for the electromagnetic perturbation H prime, and rho Cv is the joint density of states of the conduction and valence bands. Matrix elements are expressed in terms of a dimensionless parameter called the oscillator strength, and it expresses the probability of absorption or emission of electromagnetic radiation in transitions between energy levels of an atom or molecule. A higher value for oscillator strength means an increased probability for absorption or emission process. The sharp peaks in the density of states of quantum wires or quantum dots means the availability of huge density of states near the band gap of the material and hence an increase of the oscillator strength. So quantum wires and quantum dots can produce sharp peaks in the optical spectra and hence an improved optical efficiency as compared to their two-dimensional and three-dimensional counterparts. While transitions happening between conduction and valence bands are called interband transitions, that happening within a band is called intraband transitions, and as shown schematically in this figure. These transitions can happen either in the conduction band where the electrons are promoted from one level to the other, or it can happen in the valence band where the holes can be promoted from one level to the other. In bulk materials, such absorption processes are known as free carrier absorption as they depends on the presence of free carriers, that is electrons in the conduction band or holes in the valence band. In the bulk, such transitions from one K level to another K level of the conduction band or in the valence band require a change of quasi-momentum as there is a small change in the momentum between these two states, and hence it becomes allowed only by coupling with lattice phonons, which can provide or take up this momentum change. So in the bulk materials, these processes are generally weak compared to interband transitions, as interband transitions do not require a change in the K value. In quantum confined structures, such as a quantum well, there are subbands characterized by different quantum numbers, and these subbands are a consequence of energy quantization along the direction of confinement. Remember the example of ants moving from one post to another through a stretched string, which we discussed in the previous class. Each of these strings corresponds to a subband. I told you that an ant can easily move along the string, while it was not possible to make a jump from one string to the other unless it has sufficient energy. A similar picture can be imagined for two-dimensional quantum structures like this along the direction of confinement. Instead of strings, now you can imagine that the two-dimensional quantum structure consists of a few numbers of plain sheets. Each one is separated from the others by a finite gap between them. Jumping of an from one such plane to another one now corresponds to an intraband or inter-subband transition. Thus, for the conduction band, an electron can make a jump from one sublevel to another without changing its two-dimensional quasi-momentum k. As the energy level separation between the subbands are usually smaller, these new transitions happens in the infrared region and have been utilized to produce inter-subband detectors and lasers such as quantum cascade lasers. Keep in mind that these inter-subband or intraband transitions still require the presence of carriers in the conduction band or in the valence band. The absorption coefficient for an intraband transition increases rapidly with decreasing width of the quantum well. However, as the well size becomes small, the electronic states are no longer confined within the well, which produces a leveling of the absorption coefficient. Quantum confinement of electrons and holes also leads to enhanced binding between them and thereby produces increased exciton binding energy compared to the exciton binding energy for the bulk sample. Coulomb interactions between free electrons and holes in a two-dimensional system is 4 times that in the three-dimensional system. Strong binding produces excitonic states just below the band gap, giving rise to sharp excitonic peaks at temperatures where the exciton binding energy is higher than the thermal energy. Thus, excitonic resonances are very pronounced in the quantum confined structures. In the strong confinement conditions, it can be seen even at room temperature. For example, this figure shows the optical absorption in two-dimensional molybdenum disulfide at room temperature, and it is characterized by excitonic absorption. The absorption spectra of gallium arsenide, aluminum gallium arsenide quantum wells of different widths are shown in this figure. You can see that the spectrum of a thick quantum well is essentially like that of a bulk gallium arsenide. Since excitonic states are just below the band gap, there is a fair amount of optical absorption that happens just below the onset of the bulk density of state. Another point is that this absorption band is very narrow, as it corresponds to transition to a narrow level, not to a band. For a much thinner quantum well, the quantization effects can readily be seen in the spectra. You can see that the width of the excitonic absorption peak increases as the density of states of excitonic levels are higher near the band edge, as shown here. Each of these peaks corresponds to the transitions to various energy subbands. Selection rule states that only transitions between the states of the same quantum number in the valence and conduction band are allowed. This rule follows from the fact that the optical absorption strength is proportional to the overlap integral of the conduction and valence wave functions. Note that in quantum wells, the electrons and holes are still free to move in the directions parallel to the layers. Hence, we do not really have complete discreteness in the energy states for electrons and holes in the quantum wells. We have instead sub-bands that starts at the energies calculated for the confined states. The electron in a given confined state can in addition have any amount of kinetic energy for its in-plane motion in the quantum well, and so it can have any energy greater than or equal to the simple confined state energy for that subband. The density of states for motion in the plane of the quantum well layers turns out to be constant with energy. So the density of states for a given subband really is a step that starts at the appropriate confinement energy. Optical transitions must still conserve momentum in this direction, and just as for the bulk semiconductors, the optical absorption must still therefore follow the density of states. Hence, the optical absorption in a quantum well is a series of steps with one step for each quantum number n. For each subband, the sharp peak again corresponds to the excitonic transitions, again just at the subband edge. Here, transitions having subband indices n is equal to 4 can be seen. Hence, up to n is equal to 4, the electronic energy states are bound states or quantized states. For an even thinner quantum well of width about 40 nanometer, the spectrum exhibits a shift of features towards higher energy, and separation between the transitions corresponding to different subbands increases. In addition, for the thinner sample, the n is equal to 1 absorption shows some features. This splitting corresponds to the absorption involving heavy and light hole bands. Since these holes have different masses, there are actually two sets of hole subbands with different energy spacings. The light hole subbands, because they have lighter mass, are spaced further apart. The consequence for optical absorption is that there are actually two sets of steps. The heavy hole to conduction band set starts at a slightly lower energy and is more closely spaced than the light hole to conduction band set. The heavy hole set is usually dominant when we look at optical absorption for light propagating perpendicular to the quantum layers. Another property change due to the quantum confinement is the increase of transition probability in indirect bandgap semiconductors. You know that optical transitions for an indirect bandgap semiconductor requires a change of momentum and thus involves the participation of phonons and hence extremely weak or non-existent in the bulk indirect gap semiconductor. In the quantum confined structures, confinement of electrons produces a reduced uncertainty delta x in its position and consequently produces a larger uncertainty delta k in its quasi-momentum. The confinement therefore relaxes the quasi-momentum k selection rule, thus allowing enhanced emission to be observed even in indirect bandgap semiconductors.